Everybody, welcome back to chemistry. And so in this presentation, I want to talk about in more detail what Bronstead-Lowry acids and bases are, and then I'll go over something called a conjugate acid and a conjugate base. So as you will talk a little bit more about in a minute, what a Bronstead-Lowry acid is a molecule that can donate protons, while a Bronstead-Lowry base is a molecule that can accept protons. Now you'll notice that the definition includes the word proton. So I want to quickly remind you something I went over a couple of presentations ago about what protons are, and that you really sort of have to remember that a proton, all that is a hydrogen ion. So let me quickly go over that. So let's say you're looking at the hydrogen atom. And so what you might do is you might go to a periodic table and you would look up its symbol, which is H, and then you would see its atomic number 1. And so we use the letter Z to designate atomic number. And so Z is equal to 1. And so let's go ahead and draw a quick picture of a hydrogen atom. And so a hydrogen atom is you have a single proton in the nucleus of the atom. So there are no neutrons here in the nucleus in most hydrogen atoms. But we're talking about a hydrogen atom which is neutral. So not only does it have a proton in the nucleus, but it also has an electron that is kind of further out. And so here is the good old electron here. And so it's a certain distance away, usually in the first energy level. Okay, so this is the neutral hydrogen atom. So the reason why it's neutral is because it has one positive charge and one negative charge, and basically they cancel each other out. Now, another way we can represent this hydrogen atom is with an electron dot symbol. So we write the elemental symbol for hydrogen there, and then we have to remind ourselves that this thing has one electron. So there we go, we put in the one dot for the one electron. So this is the symbol for the hydrogen atom. So let me just write hydrogen atom. Okay, so now imagine that we were to hit this with a lot of energy and we were to ionize the hydrogen atom. What would happen? Well, what would happen is, you see this electron here? If you hit it with enough energy, this electron will go flying off. So the electron goes flying off like this. And let's think about what we're left with. Well, we're left with just the proton. There's nothing else there. Now, this is still hydrogen here. It has an atomic number of 1 because it still has one proton, but it no longer has an electron. So how would we represent this with a symbol? Well, here we have the hydrogen atom with its one electron here, but as you can see, that one electron goes flying off. And so here we have a hydrogen, but the electron is gone, so there's no dot here. So this is the hydrogen ion. But to remind us that this is in fact an ion, we have to tell ourselves that since it has lost that electron, now the hydrogen ion has one less electron than normal, and so it's going to have an extra positive charge due to the proton. So we put a plus here. So what I'm hoping you can see is that the hydrogen ion here, all it is the proton. So a hydrogen ion is a proton. So keep that in mind when I'm going through the description of Bronstead acids and bases. So let me erase this really quick. Okay, so the definition of a Bronstead-Lowry acid is a molecule that is a proton donor. So here we're talking about Bronstead-Lowry acid. So I'm just going to write B-L acid. And so I'm just going to indicate is molecule donates protons. And so again, a proton is just a hydrogen ion. So let me give you an example of a molecule that's a Bronstead-Lowry acid. And so that would be hydrochloric acid. And so we write HCl like this. So to create hydrochloric acid, what we would do is we would bubble in hydrogen chloride gas into water, and that creates hydrochloric acid. And this will react with water. And so what will happen is you will immediately get products. And what you'll see is that the hydrogen here in the form of an ion will break off the chlorine and stick to water. So you imagine a hydrogen sticking to water here you're going from H2O. You're adding a hydrogen ion to it, so it goes up to H3O, and because you're adding a hydrogen ion, this hydronium, which we talked about before, H3O, is a positively charged. Now, imagine what hydrogen chloride would look like without the hydrogen ion. Well, it's just going to look like a chloride ion, right? So I'm going to write plus Cl minus here. So HCl is a Bronstead-Lowry acid. Now, to really understand that here, what this HCl molecule is doing is it is donating not a hydrogen atom, but a hydrogen ion, which is a proton. What I'm going to do is I'm going to draw Lewis structures for these molecules, so I'll be right back with you. Okay, so what I've done is I have drawn some structures here that represent this reaction. So these are not exactly Lewis structures because we don't have lines for shared pairs of electrons. Really, these are sort of electron dot structures, which I think better explain what's going on. So you might remember that we said that HCl here is going to be a Bronstead-Lowry acid because it's going to donate a proton here. It looks like it's going to donate it to water. So let's focus in on the Lewis dot structure of HCl. And so I have chlorine's 7 valence electrons as X's here. I have hydrogen's 1 valence electron as a red dot there. And so what I want you to notice is here what's going on is you don't have a situation where you have, say, a hydrogen atom here with its electron. So this is a hydrogen atom binding onto water, right? Because you can only have 2 electrons here in the bond between oxygen and hydrogen. So that you don't have a hydrogen atom transfer. So instead what is going on is you see this hydrogen, this letter H here, think of this as the proton. The proton without its electron, the proton leaves. And so here now we have hydrogen sticking onto the water molecule. And so when that happens, you get hydronium. So the hydrogen ion or proton has stuck onto the water, and you will notice that the hydrogen atom left its electron with chlorine. So when chlorine picks up the electron, it is no longer a neutral chlorine atom. It has hydrogen's electron, so it's chloride. So I'm hoping these pictures sort of, again, explain it's not so much here the hydrogen atom that is transferring to water. It is a hydrogen ion, a proton that is transferring to water, as being donated to water to form hydronium. Okay, so I'm going to erase this really quick. So just to note that there are a lot of other acids that are Bronstead-Lowry acids because they can donate protons to other molecules. So another example of a Bronstead-Lowry acid is something called nitric acid. So the formula for nitric acid is HNO3. And so this can be dissolved in water. So HNO3 is the acid. And so there is the water. Now let's go ahead and see if we can predict what the products of this reaction will be. So this is a Bronstead-Lowry acid. And it'll donate its proton. The proton here is just a hydrogen ion. So the hydrogen ion will stick on the water. Can you predict what you're going to get? You're going to get hydronium, H3O plus the nitrate ion. Okay, so I'm going to erase all this and I'll talk a little bit about Bronstead-Lowry bases. Okay, so while a Bronstead-Lowry acid is a molecule that donates a proton, a Bronstead-Lowry base is kind of the opposite. What it is a molecule that accepts a proton. So let me write here that Bronstead-Lowry base accepts proton or protons. And again, just to remind you that the proton is just a hydrogen ion. So let me give you an example of a reaction where we can see a Bronstead base at work. So here we have the molecule ammonia here, which is NH3, and it will react with water to produce hydroxide, which is OH minus, plus the ammonium ion. So just to make clear, this molecule here as a reactant is ammonia, spelled A-M-M-O-N-I-A. When you stick another hydrogen ion onto it, so you get NH4+, this is a polyatomic ion. It's NH4+. It's called ammonium ion. So you can see the spelling is a little bit different. And so here, I'm hoping you can see is that ammonia is a Bronstead-Lowry base. And so what we might imagine going on is that for some reason here, the NH3 to be a Bronstead-Lowry base must accept a proton. So here you can see perhaps that the water molecule here is releasing one of its hydrogens in the form of a hydrogen ion. That hydrogen ion sticks on NH3. You have NH3 plus H plus, which is a hydrogen ion, gives you NH4+. Now imagine what water becomes after a hydrogen ion breaks off. Well, it's going to lose a hydrogen and a positive charge. So if it loses a hydrogen, you've gone from H2O to OH. So this is hydroxide. You may remember that this is hydroxide, and it'll have a negative charge. And again, I want to reinforce the idea here that ammonia is not so much accepting a hydrogen atom, but a hydrogen ion. So I'll get back with you with some Lewis dot structures. Okay, so what I've done is I've drawn out some electron dot structures for this reaction. So what I want you to now pay attention to is what this ammonia molecule accepts. Does this ammonia molecule accept a hydrogen atom, or does it accept here a hydrogen ion? So let's imagine if it accepted a hydrogen atom, what you would get. So here might be the hydrogen atom trying to bind here to nitrogen here, but you can see here it already has a lone pair here. So this electron in the hydrogen atom cannot be a part of this bond. You cannot have 3 electrons in a bond. You can only have 2. So this cannot happen. So what happens here is that the hydrogen atom will leave its electron on water, and then this hydrogen ion, which is a proton, that's the thing that will stick on to ammonia. And so when it does, you have the hydrogen ion sticking on ammonia, and so now this thing you see here is going to have a positive charge, and so this is the ammonium ion here. And so let's think about what happened to water when it lost the hydrogen ion. Well, again, the hydrogen atom left its electron here with water, so that electron is still there. So now this thing has extra electron, and so it'll have a negative charge. And so this is hydroxide. Again, so the major point here is that here ammonia is not accepting a hydrogen atom. It is accepting a hydrogen ion, it's accepting a proton. So that is a Bronstead-Lowry base. And so I'm going to erase this. I'll be right back. Okay, so I have another reaction there. So here we have hydroxide. And so this is a Bronstead-Lowry base. I may tell you that. And then here now it's reacting with this molecule here, which is called hydrosulfuric acid. It's H2S. And so can you predict the products you get here if I tell you that this hydroxide is a Bronstead base? Well, here we have to imagine that this hydroxide must accept a proton from the other molecule, right? So this other molecule is H2S. It's going to lose a hydrogen ion or proton, and it'll bind to the base. And what will you get? You get water. And then what is hydrosulfuric acid without a proton? Well, it's going to be, you're going from H2S down to HS, and it'll have a negative charge. And so that's what you would expect the reaction to be. Okay, so what I would like to do is let me go ahead and increase the slide. I want to make a very important point about Bronstead-Lowry bases. So you can increase the slide. So a very important point to make about Bronstead-Lowry bases is that these are molecules that must have at least one lone pair. So if the molecule has one or more lone pairs on it, it can act as a Bronstead-Lowry base. And so with one of the last reactions I was talking about is we have here ammonia reacting with water, and so ammonia here is acting as a Bronstead-Lowry base, and you get hydroxide and ammonium as products. So very importantly, the structure of ammonia is this here. This is NH3, and I want you to notice here that there is a lone pair on this molecule. Again, for it to accept a proton or a hydrogen ion, it must have a lone pair. And I think you can sort of see the reason why. Let's see what we can imagine what would happen when you take this molecule here with the lone pair, and what we're going to do is we're going to imagine a hydrogen ion breaking off water here, and the hydrogen ion is going to bind like that. And so what this is now is that pair there now serves as the bond with the hydrogen ion you just got. And so now that positive charge from the hydrogen ion is just distributed throughout the molecule, and you get that. So now let me explain why it's absolutely necessary for ammonia to have this lone pair here. So maybe the best way to explain it is to imagine, say, ammonia did not have this lone pair there. So we'll erase that. Now, if you have a hydrogen ion, can you form a bond between the hydrogen ion and the nitrogen? And the answer is no, because there is no lone pair here that can form a bond between those two atoms. So you must absolutely have a lone pair there. Okay, so another example of this, we have another reaction here, which is this one here. We have a reaction with the hydroxide ion with here hydrosulfuric acid, and it reacts to form water and the hydrogen sulfide ion. And so hydroxide is a Bronstead-Lowry base, and so you might expect that it must have lone pairs, and it does. You can see there's not just one lone pair on hydroxide, there are three. And so all Bronstead-Lowry bases must have some kind of lone pair. So now I want to make the important point that you can go ahead and mix Bronstead-Lowry acids and bases together as reactants. And so you probably recognize HCl here as a Bronstead-Lowry acid, and you probably recognize ammonia as a Bronstead-Lowry base. And so you can bring those two things together and they will react. And as you would expect, the acid here, what it'll do, the HCl will lose a hydrogen ion or a proton, and this hydrogen ion will travel to the Bronstead-Lowry base that will accept the proton. And so what do you get after that happens? And the ammonia picks up the hydrogen ion, you get ammonium, and then HCl, after it's lost the hydrogen ion, gives you chloride. So here I'm just stating that the Bronstead-Lowry acid, which is HCl, donates a proton to the Bronstead-Lowry base, ammonia, which accepts it. This gives us the products. However, whenever you see a reactant that is a Bronstead-Lowry acid, the chances are that the other reactant acts as a Bronstead-Lowry base. So here you probably recognize at this point that here HCl is a Bronstead-Lowry acid. So the question is water here, this other reactant, is it somehow acting as a base? And we can sort of check that to see. The way we check that is we know it's acting as a base if it's accepting a proton in the reaction. So we can check that. And so I think what you can see is you can easily imagine that hydrogen ions are breaking off here and sticking on the water to form hydronium, and HCl without the hydrogen ion is chloride. So yes, water is accepting a proton from HCl. So water here in this reacting is a Bronstead-Lowry base. So whenever you have a reaction and you identified a Bronstead-Lowry acid, the chances are the other reactant is going to be acting as a Bronstead-Lowry base. So here I'm just kind of pointing out here what I just said. Okay, so now if you see a chemical reaction with a Bronstead-Lowry base, the chances are is that the other reactant is acting as a Bronstead-Lowry acid. So let me make that point here. So here you probably at this point recognize ammonia as a Bronstead-Lowry base. So the question is this other molecule, which is a water again, is it really acting as, in this reaction, a Bronstead-Lowry acid? And the answer is yes, because if you look at the products here, you can see that what must have happened is that water must have donated its hydrogen ion to NH3 to give you NH4, and then after water donated its proton, you're left with hydroxide. So yeah, this is a Bronstead-Lowry acid. And so one of the important things that you have to get used to is, depending on the reaction, sometimes the molecule will act as an acid, but in other reactions it may act as a base. And so we see a great example of that here. Here in this upper reaction here, we saw water acting as a Bronstead-Lowry base, but in a different reaction it actually acted as an acid. So you sort of have to determine which one it's acting as. So now I need to mention to you what is a conjugate acid and a conjugate base. So a conjugate base is the molecule that results from the acid losing the proton. A conjugate acid is the molecule that results from the base gaining the proton. So here we can imagine that HCl, as you might expect, is acting as the Bronstead-Lowry acid, and ammonia, NH3, is acting as the Bronstead-Lowry base. And so here on the product side, you have the conjugate acid and the conjugate base. And so let's see if we can figure out which one is which. And so the conjugate base is the molecule that results from the acid losing the proton. So here is the acid, right? It'll lose its proton here to ammonia. And so what do we get after it loses its proton? We get that. So this thing here is the conjugate base. Now let's identify the conjugate acid. A conjugate acid is the molecule that results from the base getting the proton. So here is the base, right? And again, you're going to get the proton from the acid. So what is the molecule that you get after this base gets the hydrogen ion or the proton? You get this. So here, this must be the conjugate acid. And so you will have to be able to identify those molecules on a homework assignment or a test. So here I have some final problems. Here for these three reactions, identify the Bronstead-Lowry acid base, conjugate base for each of the following reactions. So if I can decrease the slide. Okay, so you're going to have to get comfortable with doing this. And so let's do these three questions. And so the first reaction, I have HNO3, which is nitric acid, and it's reacting with NH3, which is ammonia. And then they react, and they form NH4 plus, which is the ammonium ion, and we get nitrate ion, NO3 minus. And so you have to figure out what the acid base, conjugate acid, and conjugate base is. And so here's the way you do that. So reactants are either acid or base. Products are either conjugate acid or conjugate base. And so what I suggest you do first is look at the reactants first, figure out which one is the acid, which one is the base. Then we can go ahead and look at the products and figure out which one is the conjugate acid, conjugate base. So here we go. So we're going to focus on the reactants. And so to identify the Bronstead-Lowry acid, you have to figure out which of these two molecules here, HNO3 or NH3, donates a hydrogen ion or a proton. And so the only way you can figure that out is by examining the products. So here's the question. Is it so much that ammonia here, NH3, is losing one of its hydrogen ions and it's sticking on to HNO3 to form H2NO3? Is that what's going on? Doesn't look like it. It looks like rather what's happening here is that HNO3 is losing this H here, this hydrogen ion, and what it's doing, this hydrogen ion, is sticking on to NH3. NH3 plus H ion gives you NH4 plus. So here it looks like this molecule here is the hydrogen ion or proton donor. So this is the Bronstead-Lowry acid. The other reactant, which is accepting the hydrogen ion or proton, is the Bronstead-Lowry base. Okay, so far so good. Now you have to figure out which of these two is the conjugate acid and the conjugate base. And so you might remember that the acid, what it becomes after you remove the proton, becomes the conjugate base. So here we have the acid, we remove proton, it becomes nitrate ion here. So this is the conjugate base. So you might remember what the conjugate acid is. And so that is where you have the molecule that is the base and what it becomes after it accepts a proton. So here the base, NH3, accepts a proton, becomes NH4+. So what NH3 becomes after it accepts the proton, this NH4+, is going to be the conjugate acid. Okay, so let me move on to the next one. Okay, so the next one, let me write out the reaction. We have the hydrogen sulfide anion reacting with this molecule, which is HClO4. This is called perchloric acid. And so what happens is you get hydrosulfuric acid, which, by the way, is different than sulfuric acid. This is hydrosulfuric acid. We might talk a little bit more about that later. And then here we get the perchlorate ion. Okay. So again, how do we solve this problem? Well, first we go to the reactants and figure out which one's acting as an acid, which one's acting as a base. So this is a little tricky because here you can see both molecules have a hydrogen ion potentially that could be donated. So you have to figure out, is it HS minus that's donating its hydrogen to perchloric acid, or is it hydrogen leaving the perchloric acid and being donated here to the hydrosulfide ion? And so I think if you look carefully at this reaction, what you'll see, it looks like, is that you see this hydrogen ion here in perchloric acid, it is going to leave. And when it does, it sticks onto HS minus, and then if you have hydrogen adding on to HS minus, it becomes H2S. And then after the hydrogen ion leaves the perchloric acid, you're left with chlorate. So it looks like here that this perchloric acid is really the Bronstead laurate acid. And so the other molecule that is receiving this hydrogen ion proton from perchloric acid is the Bronstead laurate base. All right, so far so good. Okay, conjugate acid. The conjugate acid is what results when the base receives the proton. So here's the base, it's getting the proton, it becomes H2S, and so this will be the conjugate acid. And then the other molecule, well, that would be probably the conjugate base, right? Because you might recall the conjugate base is what the acid becomes after it loses its proton. So here it's losing its proton, so this is the conjugate base. Okay, so let's do one more. Okay, so for the final one, this is kind of a fun one. So we have one water molecule reacting with another water molecule, and there is a reaction that occurs. And so you'll notice there in that equation that it looks like it is a reversible reaction, so we can also put the reverse arrow there if we want, that's fine. And then what are the products for the forward reaction? Well, it's going to be hydronium and hydroxide. All right. So now you get to figure out which one is the acid and which one is the base. Okay, this is a little kind of interesting. So I think what you can sort of see, it could be that this left water molecule could be the acid. And so let's imagine what's going on here. Well, what could be going on is that this hydrogen is leaving and sticking onto this water to form hydronium, and then what you're left with is hydroxide. So the left molecule could be an acid, but the right water molecule could be an acid too, right? It may be this one that's losing its hydrogen ion sticking to the left water molecule, and so you're getting hydronium and hydroxide. So really, they're both the same molecule. One is acting as an acid and one is acting as a base. So it doesn't really matter which one you pick to be the acid or the base. Just as long as you pick one here as being the acid, the other one is being the base. And so that's fine. And so here, let's acknowledge that by indicating here that a hydrogen ion is leaving this water molecule, so it's serving as an acid, and then this water molecule is accepting the hydrogen ion, and so if it's accepting the hydrogen ion, it is a base. All right, conjugate acid, conjugate base. And so what the acid molecule becomes after it's lost a hydrogen ion is hydroxide. So this will be the conjugate base. And here, what the base becomes after it has gained a hydrogen ion is going to be hydronium, right? So we have water gaining the hydrogen ion. It becomes H3O. So this is the conjugate acid. Okay, thank you for listening to that presentation. We'll see you next time.